So the computers, the generations of computers, modern computing really started in the 1940s with World War II. And originally we stored our on-off states with vacuum tubes. And you can look up images of like ENIAC, right? And these are like these really old computers from like science fiction movies. But they used vacuum tubes to store on-off states. And so here are pictures of vacuum tubes, right? And those could be checked. Is it in an on state or is it in an off state? And anyhow, right, like the first computer, the ENIAC, had 18,000, that's it, 18,000 vacuum tubes which could be checked in an on-off state. And then the second generation computers went from vacuum tubes to transistors. Oh, but first I got to tell you, Grace Hopper debugging, right? Wait, where'd it go? Debug. There we go. So moths used to fly into the old computers with vacuum tubes because vacuum tubes were hot and they gave off light, and moths loved that. And so the moths would fly into the computer, and then they would short out the vacuum tubes, and so they would have to go in and debug the computer. Isn't that a trip? They'd actually have to pull the bugs out of the computer. So that's where we got the phrase debugging, getting the bugs out. Cracks me up. So the first generation computers were all vacuum tubes. That's where we stored our on-off state. Second generation computers were transistors, right? And so we went from vacuum tubes, which would burn out and ran hot and attracted moths, to transistors. And transistors didn't burn out. They were way smaller, right? Like this is the size of a quarter right here, and so a lot smaller, right? Like this would be smaller than a penny right here. And I'd be able to pick it up. I'd hold it in my hand about like that. But they ran cool. You could check them if it is in an on-off state, and they were a lot smaller. And so we started to be able to check a lot more circuits. Are they in an on-off state? And we could start to store stuff. I'm storing the letter A in these 4 light bulbs, circuits, switches, transistors, whatever you want to call them. I'm storing it right here, and they're in this arrangement, so that's the letter A. And literally, when I hit A on my keyboard, there's like 8 switches or 16 switches that go into a certain configuration of on or off to store that letter A. I mean, that's where it really gets mind-blowing, the scale of it. Like, holy cow, there's so much going on. So first generation computers were vacuum tubes, second generations were transistors, and then third generations we went from transistors to integrated circuits. And you could also think integrated circuits as chips, right? And so here's like a chip. And what's inside that chip, what's inside that integrated circuit is a chip, silicon wafer, right? And so here's a silicon wafer. And if you look at silicon wafer closely, so whoa, like check it out. Here this guy's holding a silicon wafer, and on that silicon wafer, they print them onto one big chip, right? They print them on one big wafer, one big board. And by the way, they make this out of sand, like they make this out of the same stuff that they make fake breasts out of. Silicon, that's it, right? Like, what an amazing substance. Fake breasts and computers. Silicon wafers. So here we have silicon wafers, and they print them all on one big chip, and then you look, and these chips are a bunch of squares, and then they cut out each one of these. So these wafers have a bunch of chips on them. They print them on one big wafer, and then they cut these chips out. And each of these chips can have billions of circuits which can be in an on-off state. So that's a phenomenal accomplishment of humankind, right? We went from vacuum tubes, which were these large things about the size of a light bulb, to transistors, second generation computer, which were like, that big, down to silicon wafer chips, where we store on something the size and thickness of your thumbnail, we are storing billions of circuits, which we can write to and we can read almost instantaneously. Holy cow, right? So that's the third generation of computers. And then the fourth generation of computers, a microprocessor, a CPU, came out like 1969, 1970. Intel invented it. Intel doesn't stand for intelligence, it stands for integrated electronics. They were integrating electronics, and they integrated various electrical components into one place, one central location, and they called that the central processing unit. It's just like crazy when you start to see how all this stuff comes together, right? But that's what Intel did. They integrated electronics into the central location, the central processing unit, and they brought together all these things like the arithmetic logic unit, the control unit, the registers, the cache, and they put it all into one place, and they created this microprocessor. It did this processing at a really really small level, and they were contracted to develop this, but then they threw the contract away. They said, we don't want your money. We created all this stuff. We created it for you. We're giving it to you, but we're not taking payment because we're keeping this technology, and we're gonna market CPUs and see what we can do with it. And that's how Intel got its start in the 70s. And so there's this dude at Intel, Gordon Moore. Here he is. And in the late 60s, he said, you know what? I am predicting that we're going to be able to double the processing power of computers every 18 months. And since the late 70s, that has held. So you could go to Google and you can search for, is Moore's law still true, right? And you can find out if it's still true because it's starting to waver just a little bit, but then some new invention comes out and like keeps going. So, but every year the processing power is doubled. So we see that like in 1971, the first silicon wafer chip had 2,300 circuits on it, right? 2,300 circuits, transistors. All these words are interchangeable for switch, circuit, transistor. It just means something that could be on or off. But 1971, the first one had 2,300. And now if you look, right, like here in 2008, 2 billion. And if you go and you look Wikipedia, Moore's Law, right, and you look at what the current image is, because I haven't updated that slide, but here's the current image, and we're at 2.6 billion, 2011. Holy cow. And the way computers have really, like the last 5, 6, 7, 10 years, really gained a lot of speed, like here in 2007, right? Quad core, dual core, right? So we have dual core, quad core, and that's starting to come on. And so, now not only one CPU in a machine, but multiple CPUs in a machine. And this is only from 2007. And this is why Go is so amazing, right? Because right here, we started to get multiple cores in machines. And before that, we didn't. And all of the programming languages, all of the major significant programming languages were created back here, where there's only one core. So there's been no new language except for Go, which has any viability that has been created to take advantage of multiple cores, right? Except for Go. And that's why Go is awesome. So that's Moore's Law. That's the generations of computers. That's how computers work. There's Gordon Moore. It's truly an amazing story. Circuit switches, transistors, and gates, those terms can all be used interchangeably. And I'll let you pause the video right here and read this, right? Because this kind of like helps explain that a little bit. And here's like, that thing, one light, how many things can we represent? So you can pause the video here and check that out if you want. And 2 to the n is the secret to figuring that out. And so if we have 16 lights, we could store 65,000, right? And our coding scheme could store 65,536 possible combinations, right? And if we have 32 lights, it could be 4 billion. Holy cow, right? And so binary digits, when you create an acronym from that, it becomes bits. And so binary is bicycle, biplane, it means 2, right? So we're dealing with 2, and the 2 that we're dealing with is on or off, or 0 and 1, and it's a binary digit. They're digits because they're zeros or ones, and so we call those bits. Awesome stuff, man. And binary digits, that's where we get it, right? And we can measure bits. And so how do we measure bits? So 1 bit is 1 bit is 1 bit is 1 bit. That's it. It's just a single, 0, or 1. If we have 8 bits, we call that a byte. If we have 1,000 bytes, we call that a kilobyte. If we have 1,000 kilobytes, we call it a megabyte. If we have 1,000 megabytes, we call it a gigabyte. If we have 1,000 gigabytes, we call it a terabyte. And now, really, this is 1,024. And the reason it's 1,024 is because that's a multiple of 2. And we have 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. However, to keep things like kind of simple, I always just say, hey, it's 1,000. But if you want to be absolutely accurate, it's 1,024. So, but it's a lot easier just to remember. It goes from a bit to 8 bits is a byte, and then 1,000 bytes is a kilobyte. So if I have a kilobyte, a single kilobyte, how many bits do I have? That's my next question for you. If I have a single kilobyte, how many bits do I have? All right, so to answer that, like pause the video and see if you can work it out, but to answer that, and need your help, crying kids, all right, be there in a minute, right? If I have a kilobyte, I've got 1,000 bytes, and if I have 1,000 bytes, I have 1,000 times 8, or I have 8,000 bits, right? And so here is like, 1 kilobyte's 8,000 bits. 1 megabyte is 8 million bits. And you can remember a megabyte is a million because M is million and M is mega. So 1 megabyte's a million bits. That's easy. And a gigabyte's a billion, and a terabyte is a trillion. T, tera, T, trillion. There you go. So that's pretty amazing. And you can always go back to how many actual zeros and ones are in this. So when you look at an image, so let me just go look at my computer, and I'm sure I've got some sort of an image here. My pictures, sample pictures, and let's change the way we're looking at that and go to details. And, I don't see the thing, but properties. And here we have, it is 845,941 bytes. Or to figure out how many bits that is, we could bring that into here and multiply that by 8. And I think I need to take the comma out. I don't know how Google works. And so it's that picture has 6,776,528 bits, single binary digits, right? So that's like 6.7 million circuits are in some state of on or off to remember the data for this image. Whoa. There's like 6.7 million single circuits that are in some state of on or off to remember this image. Like, that's amazing. And that's really getting down to the metal. That's like how computers work. That's it right there. So, you could kind of like do these problems right here, and they're kind of good to do just to work about. So on, off, 1, 0, binary digits, bits, machine language. That's all the same stuff, right? We're talking about circuits that are in some on-off state. Machine language is just the language computers speak, which is zeros and ones. That's it. Above machine language, when we talk about programming language, we have machine language, we have assembly, and then we have third-generation programming languages, which is pretty much everything else, right? Like Python, Ruby, Go, PHP, C, C++, C#, all that stuff, Java, right? It's all third generation. So machine language, assembly, third generation language. All right, so I'll let you pause the video here and read this too, just sort of help disambiguate things, help you get a little more insight. And then here we have the power symbol, right? And that's where it comes from. 0 and 1 mean on or off. So that is it. That is it, man. That is how computers work. Those are the fundamentals. In 22 minutes and 22 seconds, you just learned more about computers than the vast majority of the human population knows. Isn't that amazing?